Measuring the exact location of a quantum particle inevitably obscures its path. As a particle narrows its position, its momentum disperses. Standard physics codifies this behavior through the Heisenberg uncertainty principle. It relies on the mathematical inequality delta x times delta p is greater than or equal to h bar over 2. While this principle serves as a foundational axiom of reality, the specific mechanical interaction that forces the particle's momentum to scatter remains unidentified. This gap stems from the Archimedean point, assuming the observer is a detached entity measuring an isolated system across a passive void. Without a physical substrate connecting them, measurement remains abstract. A true vacuum provides no medium to transfer energy or momentum. As long as the observer is treated as an external actor rather than a physical component of the system, the actual source of measurement limits will remain hidden. The Elastic Continuum Theory replaces the vacuum with the plenum, a solid elastic substrate. Particles are topological solitons, knotted lattice deformations. An electron is a single knot. The observing equipment is a massive cluster. Both share the exact same material. An external observer is impossible. Target, instrument, and observer share the same continuous medium. Measurement cannot occur from the outside. It is an entirely internal interaction. Mathematically modeling this interaction requires treating the entire experimental setup as a set of elastic deformations. The first term, U-target, describes the specific displacement field of the soliton being measured. The second term, U-probe, describes the dynamic field of the probing instrument as it moves through the plenum toward that target. U-total represents the physical reality of the measurement, the moment these two displacement fields overlap and intersect in the lattice. Because the medium is nonlinear, the fields do not simply pass through each other. The presence of the probe's geometry alters the path and shape of the target. Data acquisition is the physical result of two structural topographies colliding within the medium. By zooming into the boundary where these fields meet, we can identify the specific mechanical cost of extracting data. To retrieve information, the probe must move energy and momentum from the target through the lattice. This transfer occurs via acoustic elastic wave packets. These vibrations carry mechanical information across the solid nodes of the plenum. These waves exert physical pressure on the target structure, pushing against the lattice nodes that form it. This perturbs the local shear and bulk stress tensor of the soliton, shifting its structural geometry in response to the incoming wave packets. In a solid medium, every action triggers a reaction. The target knot deforms, and that deformation sends a reflected wave back to the instrument, carrying the data of the interaction. This interaction rules out the possibility of a zero-impact measurement. Probing a structure in a continuous lattice necessarily alters that structure. Measurement uncertainty is the direct mechanical consequence of this elastic interaction. If uncertainty is mechanical, then its absolute limits must be dictated by the material properties of the plenum itself. The plenum possesses a finite structural scale. The individual nodes are separated by a fixed distance, establishing a rigid grid. This spacing creates a high-frequency dispersion limit, a minimum wavelength this lattice can transmit. Wave packets smaller than the distance between nodes cannot propagate. They scatter against the grid, effectively disappearing. Georgiadis's fundamental precision bound maps these material constraints. The left side represents the minimum possible increments of space and momentum we can resolve. On the right, the integration volume defines the physical space where the probe and target interact. The strain energy density gradient dictates the steepest curve the lattice nodes can sustain. This gradient defines the minimum resolution of any measurement. You cannot measure a feature smaller than the deformation wavelength of the material your instrument is made of. Hyperelastic material properties of the vacuum itself establish the rigid floor for mathematical uncertainty. These microscopic interactions define the limits of observation, even at the human scale. Macroscopic instruments, like electron microscopes, are entirely constructed of interconnected displacement fields. In any experiment, billions of these coupled solitons act as a single unit, their displacement fields locking together into the solid equipment on the bench. The continuity of the plenum means there is no gap between the sensor and the particle it observes. They are parts of a single, unbroken solid. The acoustic back reaction derived in equation 2 scales to define the absolute performance limits of all technology. Every physical experiment is an internal mechanical dialogue within one solid-state continuum. We can now reconcile the standard model of uncertainty with the mechanics of the plenum. When compared side by side, the standard Heisenberg axiom and the endogenous precision bound describe the exact same boundary curve. While both equations describe the same limit, the ECT derivation defines that limit using the specific geometry of lattice deformation. This framework replaces an axiomatic limit with a derived mechanical cause. Uncertainty is the deterministic back reaction of the solid vacuum resisting the intrusion of the observer. Observation is a physical interaction, and the absolute limits of human knowledge are anchored in the mechanics of solid-state continua.